I want to take a look at this notion. It's infinity arithmetic, but we're using one-sided limits. And a good example of this would be something like this. Suppose we want to take the limit as x goes to 3, and we want to take the limit x goes to 3 from the right of the function 1 over x minus 3. The question is, what is that value? Remember what this means, where x is getting closer to 3, we're choosing values only greater than 3. So this is a one-sided limit or a directional limit, depends on how you learn to call this. We're approaching 3 from the right. What is really helpful here is the graph of this function. Very roughly, that's the graph of this function. The vertical asymptote is at 3. And so what we can say is, as x goes to 3 through values greater than 3, right, we can say this is 1 over value greater than 3 minus 3, and any value that's slightly greater than 3 minus 3. As you get closer and closer to 3 through values greater than 3, and then subtract that off, the values you're getting are getting closer and closer to 0, but you're getting closer to 0 from the right. And so the way to think of that is, we can think of this as being as 1 over 0 as we're approaching this. Again, this is a limit statement. We can think of this as being positive infinity. Everything I'm writing here is not correct arithmetic in the sense of, it's not correct mathematics in the sense of the ordinary meaning of this equal sign. But what we're doing is using this shorthand as a conduit to understand what's happening in this limit. I am not saying that 1 over 0 is a number and then that number is equal to this number. That is not what this says. That's not what this is intended to mean. But what we are saying is this. For this function, which corresponds to this graph, as you get closer and closer to 3, as you choose values on the x-axis that get closer and closer to 3, approaching only from the right, the function values here, here the function value is here, the next function value is here, the next function value is here, the next function value is here. As you get closer and closer to 3, approaching from the right, the function values recede up the y-axis. There is no boundary as to how high the function values become. That's what this is intended to convey. So this information is not the same as ordinary arithmetic, but this does convey the same information as what's happening in the picture. And so we will use this as sort of a shorthand notation with the understanding that this is not correct standard mathematics. It is a way of thinking about it. It's a way of getting your mind around these ideas, and it's a way to get the correct final result. All right? Now, suppose in the same expression here, or the same function, we want the limit as x approaches 3 from the left. Well, now what we're doing is approaching 3 using values only less than 3. And the function value here is there, then the function value is here, then the function value is here, then the function value is here. What's happening is, as you get closer and closer to 3, the function values now recede down the y-axis. There's no boundary as to how small or how large negative the function values become. And so we can think of this. This is not standard correct, but this is a way to think of it. This is 1 over number smaller than 3, close to 3, but very close to 3, but slightly less than 3, minus 3. This is a number very close to 0, but slightly less than 0. So 1 over 0 negative, we can think of that as being negative infinity. And this applies not only to this function, it applies to any other function. This sort of way of thinking about it. It's not even, I suppose you could call it this logic, but it's a way of thinking about what's happening with this picture, with this function, with this occurrence. And this is a way to, it's a bridge patched together from some basic ideas to get to the correct final result. Now, it's true not just of this function. Suppose we change the function slightly. Suppose we require this to be squared. Well, that changes the picture. One of the things that's very convenient is to have access to some sort of either your brain. It'd be nice to have access to your brain, or also to simply have access to a device that will draw the graph. So very roughly, if I play the role of a computer, roughly speaking, that's the graph of this function. This is one of the, we used to call them in basic algebra, these are like the volcano functions. And so now what this says is as you approach 3 through values greater than 3, in this case, the function value is positive. So we may say this is 1 over value bigger than 3 minus 3 squared, which is a value bigger than 0, but it's getting squared. When you square a number close to 0, it's still a number close to 0. And the key is this is still positive. This is positive infinity. If you go directly from this statement to here, I'm okay with that. Because you can get this just as easily from the graph as you can from this way of thinking about it. What is perhaps interesting here is if we take the limit as x approaches 3 from the left of 1 over x minus 3 to the second power. Now we can say this is 1 over, this is a number less than 3 minus 3, but that's getting squared. Well, we've seen a number slightly less than 3 minus 3, that's a number slightly less than 0, but that's still getting squared. And a negative number squared is a number close to 0, but it's positive. And that goes to positive infinity. And we can see that's what's happening in the graph as well. In this particular case, since the right-hand limit and the left-hand limit agree, in this particular case, we can say, this is a stroll down memory lane, we can say the unrestricted limit is also positive infinity, because if the left-hand limit and the right-hand limit agree, then the unrestricted limit is that same value. So that's a way to think about what's happening. If you know the graph of a function, then we should be able to compute or evaluate these limits. And there's nothing magic about the function we were playing with. Suppose we want the limit as x goes to pi over 2 from the left of tangent of x. Well, if you know the graph of tangent, that is not particularly challenging. Very roughly, that's the graph of tangent of x. And as you approach values, if you approach x pi over 2 from the left, these function values recede up the y-axis. This is equal to positive infinity. If we take the limit as x approaches pi over 2 from the left of tangent of x, then you're approaching, we have to remember the rest of the picture here. This is pi, this is 3 pi over 2. We know what the graph of tangent looks like. And so as you approach values using only values greater than pi over 2, the function value recedes down the y-axis. We can think of this as being negative infinity. This is going to come in handy because if we have this expression and we have something involving L'Hopital's rule, then we will want to be able to say, what does this approach? If this approaches infinity and maybe some denominator also approaches infinity, then we can apply L'Hopital's rule to be able to evaluate that expression. And so these one-sided limits come into play. It is particularly convenient. I'm sorry, this was positive. I'm sorry. What I've said is not correct here. I should have had a plus here, where I said positive and I didn't write. As you approach, let me say that again. As x approaches pi over 2 from the right, the function value goes to negative infinity. All right? Anytime you have a vertical asymptote, this structure can be assisting, can help you. There's one in particular that is convenient to have in mind. And that's the natural log. Now I gotta be careful here with my bad writing here. This is limit of the log. Now we know what the natural log function looks like. And as you approach 0 from the right, the natural log function recedes down the y-axis. That's negative infinity. If we want to take the limit as x approaches 0 from the left of the natural log function, this has no value. Because natural log is not defined for these values. These values are not in the domain of natural log. Another way to say it is, as you choose values that get close to 0 but are consistently negative, less than 0, what happens to the natural log function? What we're saying is nothing happens to the natural log function because it's not defined for those values. So as you get closer and closer to 0 on the x-axis, what is happening on the y-axis? Nothing, because this picture is not defined here.